Hi kids, I wanted to show you some examples from section 10.3 to help you do the practice problems. So here they are. In this particular section, they sprinkle in some examples that are not use substitution. So I kind of marked them on here, but you won't see them marked on your notes. When I look at this, this is a use substitution. You've got a square root. You know that your u is going to be what's inside the square root, and then you can do all your steps with that. This one though, see how it's only a single piece? It's not going to be a use substitution, so you can just directly find that integral. These are, assume that you're going to do them by hand and not using your calculator. So numbers 1 and 2 we're not going to actually do together. I want to pick up with number 3 as our first one that I'm going to do with you. Here it is. Evaluate the definite integral. We're going to try to do these without a calculator. All right, so job number 1, I need to figure out what my u is. And normally if you have an e to the x situation, your u is going to be the e to the x. That means that du is e to the x dx as well. All right, then I got to think about the bounds, right? Because this is now a definite integral. And if u is e to the x, then I have e to the first as my upper bound because my upper bound's a 1. E to the first is just e. And if I look at my lower bound is a 0. So I have e to the 0, and that's 1. And now I'm ready to put my integral together. So I have the integral going from 1 to e. And if you remember, e is about 2.718. So that means that the bigger bound is on top, but I don't have to do any changing. And if I do my substitution, e to the x dx is my du. And this would be 4 minus u in parentheses. So I have 4 minus u, and then the e to the x dx is du. And so that's my situation. So now I'm going to take the integral of that. And so the integral of 4 is going to be a 4u. The integral of a u is add a power on, so that makes it u squared, but divide by the power. So 1/2 of u squared. And that's going between 1 and e. And so then I plug in my f of b minus f of a. It's going to look a little odd, right? Because I've got e's in there, but it's okay. I got 4e minus 1/2 of e squared. That's my f of b. F of a is if I put a 1 in. 4 times 1 is 4. 1 squared is 1 times 1/2 is minus 1/2. And so I get this funny looking thing, right? I can simplify a little bit better, make it slightly prettier. The 4e I can't do much with. The 1/2 e squared I can't do much with. But this, if I take 4 and I subtract 1/2, that's 3 and 1/2. And so I'm subtracting away 3 and 1/2. Sometimes you might see that as 7/2. Mr. AP doesn't really care either way. 7/2 is 3 1/2, and there you go. That's example number 3 with an e. Number 4 is another u substitution. Obviously inside your parentheses is an x squared plus 1, that's your u. Number 5 is not a u substitution, and I would give you the hint of think of your inverse trig functions and see if you can integrate that one based off of that. Number 6 is a integrate with u substitution. Inside your square root is your u. Number 7 is another one, 7 here it is, that's not a u substitution. Let me start you on the first step for this guy. It is the integral going from 3 to 6. If I divide x into x squared, I get an x. If I divide x into 2x, I get a 2. And that is the same exact thing as what the original integral is. It's just simplified. Number 8 is a u substitution. Number 9 is not a u substitution. You're going to use your regular integral rules for trig functions. Number 10 I do want to do with you though. And number 10 again has ln's involved and e's and such. I figured you might pick that one because of it being a little more intimidating with those features. So in this case I'm going to let my u equal the ln of x. And if I take the derivative of the ln of x, I get 1 over x dx. And that makes me kind of happy because look at where that x is. It's in the denominator, which is where this one is. So if I take my bounds and come up with my new bounds, I have u equals the ln of my upper bound is e. And if you remember that rule, hopefully you do, the ln of e is just 1. If I go to my lower bound, the lower bound is going to be the ln of 1, and the ln of 1 is 0. If you're not sure, you can check it on the calculator, but that's the truth. Anything to the 0 power is equal to 1. E to the first power is equal to e. That's kind of what it's talking about, if you remember back doing the loops and things back in pre-calc. All right, so let's put our integral together, see what it looks like. The integral is going from 0 to 1. And I have the ln of x, well, that's my u. 1 over x dx is my du. And that's it. Look at how simple that turned out. So if I take the integral of u, I have to add a power on and divide by the power. That's going to make it 1/2 of u squared. And I need to evaluate that going from 0 to 1. So if I f of b this, it's 1/2 of 1 squared. I guess I should, the 1/2 is attached to both things, so 1/2 of 1 squared minus 0 squared, and I end up with 1 minus 0 is 1, and 1 times 1/2 is 1/2, and that's my final answer for number 10. So if I move on to the next part, number 11 is the next one I thought might be a little intimidating to you. So again, it's going to be a u substitution. You have to pick your u, and your u is the part that's inside of the root. So x squared minus 5 would be your piece. Take the derivative of it, and you get 2x dx. And look, you don't have to divide the 2 this time because you do actually have a 2x that's in your numerator. So 2x dx is going to be your du, and you've got the square root of u in the denominator. That's going to be our setup when we do the substitution, but let's talk bounds before we do that. My bound is u equals x squared, the square root of 30, my upper bound, squared minus 5. Squaring that square root gets rid of the root, so it's really just 30 minus 5, or 25. And my lower bound, if I put a 3 in there, is going to be a 3 squared minus 5. That's 9 minus 5, or 4. So there's your new bounds. And we're going to put our integral together, going from 4 to 25. And I end up with a 1 over the square root of u. That's it. And then I have my 2x dx is my du. Now, in order for us to integrate, it's going to be easier for me not to have this as a root, so I'm going to change it into its power, fractional power. I have an integral going from 4 to 25, but this is really like u to the negative 1/2 du. It's a square root, but it's in the denominator, and therefore you gotta kind of say that. So in looking at this, if I add a power onto that to take the integral, adding a power on is going to be to the positive 1/2 power, but then it's divided by 1/2, so it's really going to equal 2 u to the 1/2 power, and that's what I'm going to evaluate going from 4 to 25. You can take the 2 out if that makes your life a little happier. U to the 1/2. Going from 4 to 25. Well, it turns out your bounds are really sweet, because if I take this, the square root of 25, or I'll write it out the longer way, this is 25 to the 1/2 minus 4 to the 1/2. If I take the square root of 25, that's 5. 2 times 5. The square root of 4 is 2, and so 5 minus 2 is 3. And if I take 3 times 2, I get a final answer of 6. And that's that one. Last one I want to do is number 13. Number 12 is actually a u substitution that works pretty nicely. You're going to take what's inside the square root and use that as your u. But number 13 actually comes out, it's not going to be a u substitution. And I know you usually pick for me the ones that are the trig functions. And I can see that this guy is not going to be any type of u substitution thing, because it just doesn't fit the bill. You don't have a chain rule that you're trying to undo. You just have 2 individual pieces. So here's one where the chain rule doesn't apply. That means I don't have to play with the bounds, and I can just take the integral of each piece. So if I take the integral of a 2 sine of x, that's going to be a negative 2 cosine of x times 1, technically, times the derivative of the angle, but it's just a 1. So I got a negative 2 cosine of x. And this guy over here, if I take the derivative of sine, it's going to be, this is technically a plus sign here from this plus sign. This is going to be a negative cosine of 2x, cosine of the same angle, but because it's an integral, I'm going to be dividing by 2 on that piece. And then I'm going to evaluate this going from 0 to pi. All right, so let's see if I can, I guess I can't really clean it up that much, can I? Maybe a little bit better. If I take, I'm debating, do you want to take out the negative 1? Let's just leave it the way it is. We're going to plug in pi. So negative 2 cosine of pi plus a negative, so this is going to be minus cosine of 2 pi over 2. That's my f of b. And I'm going to subtract this. I don't have a lot of space over here. I'm going to subtract it when I put a 0 in. So the 0 one would look like this. Negative 2 cosine of 0 minus the cosine of 0, 2 times 0, over 2. All right, let's start evaluating. Cosine of pi. Think about the coordinate that goes with pi. The coordinate at pi is the coordinate negative 1, 0. Cosine's the x value. So I have negative 2 times negative 1 gives me a positive 2. Minus. Then I have the cosine of 2 pi. Well, 2 pi is the coordinate 1, 0. Cosine is the x value. So I have a 1, which is this thing, over 2. So minus 1/2. If I go to 0, well, 0 has the same coordinate here. So cosine of 0 is 1. Negative 2 times 1 is negative 2. And this one's kind of nice too because it's still 0, right? So 0 is still this coordinate. It's a 1, so it's a minus 1/2. And if I put all these lovely things together, I have 2 minus 1/2 plus 2 plus 1/2. And because I have a negative half and a positive half, they can cancel each other out, and I no longer have fractions. And look at that, 2 plus 2 is 4. All right, how easy calculus is, right? You're going to skip number 14. It gets into some crazy substitutions that I don't think you really need to get into at the moment. So those are my extra practice problems for the section 10.3. And we only have one more section to go, section 10.4, and then we'll be done all the content we need to cover. So hope you're all doing well, and I'll talk to you soon. Email me if you've got any questions. Bye.